Shall we continue? Okay, so I think we are talking about like how to design a reinforcement learning agent that can do more than one task, right? Like, so where task is defined as an MDP, right? Like, so now the task distribution like can be of any type, right? Like, so for example, the grid world example that we saw is like a very close family of MDPs, right? Like, so like it is all same MDP except for the fact that start and goal are different, right? Like, so but you can think about like really wide variety of MDPs. Like, so for example, let's take Atari. Now, there are like 50 to 60 games in Atari. Now, when we talked about DQN for Atari, like, so like I showed you a graph of performance, but that graph was for like one DQN agent trained for one task, right? So now, can I design a single reinforcement learning agent that can learn to play all the Atari games? That is a much more harder distribution of MDPs because the spectrum of Atari has like really simple games like Breakout, which has similarity with Pong, right? Like, so these are two MDPs which are very close. But it also has Montezuma's Revenge, like, so which involves walking through the room, like finding keys and like opening the door and so on, like fighting with the enemies and so on. Okay, so now can I have like one agent which can do all these tasks? So that is a really difficult problem. Now, how do we approach this problem, right? Like, so like there are a couple of ways in which we could solve this. Okay, so first is the idea of multitask RL. Okay, where you have a single reinforcement learning agent which is learned to learn multiple tasks, but this time simultaneously. Okay, like if we go back to this grid world example that I gave, so this is kind of an example for multitask RL. Okay, because you have many tasks here, and in every episode you randomly sample a task. Sometimes you have the luxury to sample, like sometimes it is given to you. But as long as you see all the tasks, like enough number of times, like so over the training time, like you are going to generalize. Is that clear? So that is the idea of multitask RL. Like in multitask RL, like so you have many tasks, T1, T2, T3, and so on. Like, and the agent can somehow like simultaneously access all the tasks. Okay. Now, I showed you the like really nice multitask example, the grid world example, like where it is kind of obvious that seeing many tasks should help, right? Like, so for example, like if I learn in the second grid world that staying here is actually better than staying here, given that it is conditioned on the start and end goal, I am also learning something about this world. I'm also learning something about this world, right? Like, so like learning in one world, like one task actually helps me to learn in other tasks. Okay, but that is not always the case with multitask learning. Okay, so when you have many tasks to learn, okay, so you could have what is known as task interference. Okay, which could make the problem much harder. Okay, let me give you an example, like a simple grid world example, like where task interference is obvious. Okay, so imagine that I'm in a grid world, and the task is basically picking up task. Okay, so like you could have an apple which you want to pick, or let's say a box. I want to draw orange, but I don't know how to draw orange. So like, let's say there are apples and boxes. Okay, now I have a distribution of MDPs where you could have the apple and orange lying wherever in the grid. Okay, but now the reward function is also going to be a little bit different between this family of MDPs. Okay, now in half of my MDPs. Okay, getting the apple is going to give me +10. Getting the box is going to give me -10. Okay, so this is for 50% of the MDPs. Now for the rest of them, like now for another 50%, okay, like apple is going to give me -10 and box is going to give me +10. Okay, now if you use the naive multitask learning strategy here, I'm not going to learn anything. Okay, so this is the averaging issue, right? Like, so like the average performance here tells you that like both apple and box has 0 value. Like probably you're going to learn a random policy, which is going to randomly pick an apple or orange. But if I don't give you any other extra information, actually the random policy is the best policy here, right? Like, so like if I don't tell you which is good, like random policy is the best policy here. However, I can slightly modify this task in such a way that when you pick an object, the episode doesn't end. Okay, instead of the episode ending, the object is going to appear somewhere else in the grid. Okay, so now we have an interesting problem formulation where, like, let's say we are in this half, apple is +10. Okay, if the agent picks this apple, then this apple is going to appear somewhere else. So you can go and pick the apple again. Let's say there's a fixed number of times it would happen. Let's say 10 times. Okay, so the maximum score the agent can get is 100. Okay, now what do you think would be the optimal performance score in this task?
90.
Is it 90?
80.
Okay.
Maximum is still 100, but that's a lucky case.
Okay.
I mean, the first time you read the positive thing,
so you want to try both
yeah.
things once, right? So which will result in a 0. Then you have 8 more times. So
try both ones, right? You just need to try the first object and the other object, you know.
Okay, yeah. So in that case, it is not 80 either.
It's 90.
So it's an average.
95.
Is the average 90?
95.
I don't think it is 90. It might be 85.
If you eat the positive reward.
So okay. So with 50% chance, whatever you found is +10.
Yeah.
Okay, which means with 50% chance, you're going to have 100 points. But with 50% point, whatever you found is wrong, in which case you have a 80. So yeah, you're right. Okay, so the average is 90. So the average performance that you could get with that strategy is 90. Okay, but the point is, this average, this strategy of like trying the first thing once and then trying the rest, right? So you can, well, I should not be very confident, but like you can almost never learn that policy with multitask reinforcement learning. Okay, because it is just going to be very hard. Like sometimes, like you have, like it is very hard when you have this averaging effect. Okay, now how do I solve? So this is an example for task interference. Like there are 2 tasks, but their reward functions interfere. Okay, now I can have 2 tasks where transition dynamics interfere. Like, so for example, like if I have to be an adversary, like I could just say that moving up is up in one MDP, but moving up is actually down in another MDP. Okay, so I can have inverse dynamics in another MDP. Now, how would I like solve these cases, right? Like if I have to give a more practical example, like sometimes opening a door doesn't hurt in one MDP, but opening a door hurts in another MDP. Okay, now this is the transition dynamics issue. Now this is going to, if you're doing averaging effect, then on an average, like you might be like not sure on like what action to perform here, right? Like so there are this task interference issues like normally when it comes to multitask learning. But this is not just the problem of reinforcement learning per se. Okay, so like this is the problem with multitask supervised learning as well. Okay, there's actually a lot of work in the multitask learning literature, like including both supervised and reinforcement learning, on like how to design like learning update rules such that they don't interfere with each other, and such that like you can still on an average learn a better like policy for all the tasks. Okay, but sometimes it might not be possible like to learn a better policy for all the tasks. So that is why there is no general guarantee that if you do multitask learning, you're going to do well in all the tasks. So there might be a like family of MDPs where I can have much better solution by just focusing on that particular MDP instead of focusing on all the MDPs. Okay. Now, this whole idea of multitask RL like is like one way to handle this problem. Okay. There is also another way to handle this problem. Okay, which is the idea of lifelong reinforcement learning. Okay, or this is also referred to as continual reinforcement learning. So there is equivalence in supervised learning. Like you can talk about having a lifelong supervised learning system or a continuous supervised learning system, but we will discuss just about reinforcement learning here. Now, what do I mean by lifelong reinforcement learning? Okay, now in lifelong reinforcement learning, like the big difference with respect to the multitask RL setup is we will not have, or we will not assume having access to the distribution all the time. Okay, so we cannot simultaneously pick one task at a time. Okay, and you have very little control over that. Like, so you're going to have the tasks coming to you in a sequence. Okay, and you will be solving these tasks in sequence with the hope that you're going to do better for future tasks based on your experience in the past tasks. Is that clear? Now, this involves like several interesting like opportunities like for coming up with general purpose like agents. Okay, like for example, like when you have an agent which is learning one task after another. Okay, so there is scope for knowledge transfer, which means there are two possible knowledge transfers here. Like, so for example, I could integrate all my knowledge so far and transfer it to the next task that I'm going to do. Okay, now to give you a practical example, like, so think about the very first time you learned to play a video game. Okay, maybe like you were like in your second grade or third grade. So like you're starting to play the first video game, like maybe Mario, like I don't know what you started playing with. And like you might have taken like half an hour, 1 hour to get used to the joystick, like to get used to the idea that, oh, I have to cross this level, like I have to do this, I have to jump like this and so on, right? Now, when you think about the amount of time that you took to learn to play the first video game versus the second video game, it's going to be exponentially less. Like, so like once you figure out how a video game works, then maybe you go to a completely different MDP, like the second video game. So instead of a walking game, it could be a car race game. Okay, so in this case, it is driving. Okay, it is very different from Mario. But still, you have an idea of like, you already have a lot of general ideas, like, oh, there is a score in the top right. So my goal is to improve the score. And there are opponents. And my goal is to avoid these opponents because otherwise I'm going to get killed. And you would already know that, oh, there are 3 lives given to me. So like I should be very careful in spending those lives and so on. So you already have a pretty good idea of like how to do the second task, even though you are seeing it for the first time. Okay. Now this knowledge transfer is what we're going to call as forward transfer. Humans are lifelong learning agents. Okay. So like we constantly learn, like, so like we learn new things and like we build upon the existing things and like use that to learn the new things efficiently, right? Now, how to do that efficiently, like with the reinforcement learning agent? So it's one of the hard problems, like, but that is what we call as forward transfer. Now we can also do the reverse of that. Okay, so we can do backward transfer, which means I'm learning a new task. Maybe sometimes this is going to give me an idea about doing one of the previous tasks better. Okay. Now, this also happens in your learning curriculum, right? Like, so as you learn new things, like you get a better understanding of old things, like, and probably like you might do the old things better, like in a more efficient way, because you have learned these new things, right? Like, so this is backward transfer. Now, the goal of lifelong reinforcement learning is to design agents that can have both forward transfer and backward transfer. Okay. Now, this kind of requires an idea of like how your knowledge is represented or integrated. Okay. Now, your knowledge cannot be just the policy network or the value function anymore. So far, if you think about all the algorithms that we have seen in this course, what is the knowledge of the agent? Okay, so the knowledge of value-based agents is the value function, right? Like, so they know how to compute value for a state. That is their expertise. Like, so they are going to use that expertise to come up with the policy. The value, like the knowledge of the policy-based agents is just the policy itself, right? Like, so like how do I act in this particular state? Now, this kind of like low level, like what I'm going to call as low level representation of knowledge is not going to be sufficient anymore. Like if you want to talk about forward transfer and backward transfer. So do you have any ideas for better representation of knowledge? We have seen something in the course, yeah?
So I think we previously talked about state abstractions and things like that, other things. And we were like giving the hierarchy by ourselves, but if that is also part of the learning process, then
Yes.
that could be like one thing where.
Yeah, so that's a good point. So hierarchy or abstraction, right, is one of the major like source for knowledge representation, right? Like, so like if I can learn options, okay, so if I can discover options on the way, okay, so then that is my knowledge base. Like, so like imagine a reinforcement learning agent. Well, this is the dream reinforcement learning algorithm. Okay, so like which starts with like low level actions. Okay, now after like experiencing a bunch of episodes, it actually figures out that like whenever it sees an object, it can actually go take it. Okay, now this idea of pickup, okay, is a skill or an option. Okay, and I can actually add this to my library of actions. Okay, so like in the case of abstractions, like I start with primitive actions, just call them as A1, A2, A3, A4. Okay, if the agent can discover new like abstract actions or temporally extended actions or options or skills, whatever name you give, okay, now I can add a new option, which is pickup. Okay, now when I learn the next task, okay, let's say the next task involves picking up the bottle. You pick up the bottle, I give you +10 reward. Okay, had I solved that problem with just this primitive actions, it is going to take me a lot of time to figure out what to do. Okay, on the other hand, if I also have access to the pickup action, probably with just few trials, let's say this table is the world, like I can do higher level exploration. I can say, okay, I'll try to pick this, see what happens. I'll try to pick this and see what happens. And I'll try to pick the bottle and I get a reward. So I solve the task, right? So learning options is one way to like represent knowledge, okay? But it is extremely hard. Why is it hard? Like, especially given the lifelong learning setting, it's hard because sometimes like you might need to learn options which are not very useful for the task in hand, but it is useful for the future task. Okay, like okay, I'm thinking about all the math that you learn in your first year of undergrad, right? Like, so like sometimes you would wonder, why do I learn about SVD? Like, why do I learn about these matrix operations and so on? Like, so, but as you take more and more advanced courses, like you will appreciate the importance of these things, right? Like, so like as you see more applications, then you realize, okay, so this is useful in some place, right? Like, so Now, in that case, like, so you are kind of building upon like previously learned concepts, right? Like, so now sometimes these concepts might not have immediate rewards. So the problem with reinforcement learning is, even though our goal is to maximize a complete return, often we only have access to the immediate reward, right? Like, so like as the reward goes farther and farther because of the issues with temporal credit assignment, like it is very difficult to pick up these like links. Okay, so it is very hard to learn, for example, that I should pick up this option today because it is going to be useful after a year. It is hard even for humans. So you can imagine how hard it is for agents, right? Like, so now in general, like this idea of like how to learn options, like is very difficult. Now, there are many ways in which one could approach this problem. Like, okay, so for example, like instead of just focusing on the task in hand, like very recently, like there is actually a lot of progress happening in the last couple of years on self-supervised learning. Okay, so this is not supervised learning, this is not reinforcement learning. It's called self-supervised learning because the agent itself will decide a goal. Okay, like, and it will try to like achieve the goal. Well, like that is not exactly self-supervised learning, but the general idea of self-supervised learning is like agent giving some form of supervision to itself instead of expecting a human to give the labels. Okay, now imagine having an agent which decides sub goals, which has nothing to do with the goal, the actual goal. Okay, like for example, forward prediction is a really good like reasonable sub goal. Okay, if your system is always getting better and better at predicting the future, okay, which has nothing to do with the policy itself, right? Like our goal is the policy, but still, if you can get a system which can predict the future better and better, then you're going to eventually become really good in making predictions about the future. So like you can learn better policies very quickly because you have a lot of knowledge. Like in this case, the entire world knowledge is kind of integrated into the forward prediction model. Okay, so that is just one example. But there are like many other examples in the literature. So I encourage you to go read more about it. Okay, but this is about knowledge representation. But there are also other challenges that one could face when you are using lifelong learning. Okay, one of the major challenges with lifelong reinforcement learning is the idea of catastrophic forgetting. Now, the fact that you are actually learning one task and then moving to the next task and then moving to the next task means that, for example, if the transition dynamics of these tasks keep changing, your network is kind of tuning itself to the current task, right? Like, so now this comes at the cost of affecting the previous task performance. Okay, so your performance in previous tasks might degrade because of this lifelong learning phenomenon. Okay, now this idea of like degradation in performance in the previous task is known as catastrophic forgetting, like because you're forgetting the previous task. And I think even humans have some catastrophic forgetting, like, so, but probably not that catastrophic, but humans have some forgetting for sure, right? Like, so, like if you learn to play piano, like when you were 10, like let's say after 30 years, like you see the piano again, okay? You haven't touched the piano for 30 years, like, so obviously you cannot play at the same level. But what is so striking about human intelligence is you just need like 1 or 2 more days, like to get back to where you were. Okay, like you forgot things, but you somehow our brain has a mechanism to bring back these memories, like if they are relevant, and it just takes time, but we can do it. But that is not the case with agents. With agents, especially when you use function approximation, when the agent forgets something, it is forgotten. Okay, so bringing it back is a very difficult thing. Like, so Now, there are a lot of techniques in the lifelong learning literature on like how to avoid catastrophic forgetting. We will not go through all those techniques today. Like, but if you are interested in like this idea of designing agents that can learn many tasks, which is sometimes also defined as the AGI or artificial general intelligence, right? Like, so having something close to humans, like how we are versatile in picking up many things, right? Like, so if you want to learn more about this and explore more, like there is actually, is it next winter? I think, yes, I think it's winter. So there is a course on continual learning or lifelong learning at UDM next term, like in winter. Okay, so which might be a good follow-up course if you're interested in exploring lifelong learning agents. Okay, so well, this is another way to handle this distribution of MDPs. Okay, so there are some questions in the chat. How much useful is the understanding of brain neuroscience structure and mechanisms applied in oral? Okay, that's a very good question. So in fact, like for a lot of higher level topics that I discussed today, there are close connections to neuroscience. Okay, so there's a lot of inspiration coming from neuroscience. Like, so like for example, like this whole idea of like temporal reference learning and like learning with trial and error, right? Like, so these ideas originated, like the trial and error learning originated from human learning studies in neuroscience. Okay, so and there is also a lot of work which shows that our brain like there's some sort of temporal difference learning. Okay, so there is a lot of biological proof for temporal difference learning happening with humans too. But even for lifelong learning, like, so how to solve lifelong learning, so there's a lot of work which are inspired by neuroscience. So I think in fact the book has a chapter on neuroscience and reinforcement learning, like, which is a very interesting read. I encourage you to read the book. But there is also a lot of work in the intersection, and there is a lot of potential applications of ideas from neuroscience to reinforcement learning. Okay, so probably we will stop here. Okay, so today's lecture was more about some of the general challenges in solving reinforcement learning, and also some of the general challenges in designing general purpose agents, right? Like, so like agents that can do many tasks, agents that can learn the new tasks faster, and so on. So I think we will stop here, and probably I will give you a bunch of useful next steps before I take questions. Okay, just give me a couple of minutes. Now, well, maybe I should have had slides for this, like, but probably I'll write some here. Like, after the lecture, I'm going to put all the scribes that I haven't put so far, so that you have access to the scribes. Okay. Now, as I mentioned, like, if you want to learn more about lifelong learning agents, like, which can learn many tasks, like, so there is a continual. I don't like the name. Like, okay, in machine learning, there are two groups of like researchers, like both calling the same paradigm, either as continual learning or lifelong learning. Okay, so I come from the lifelong learning school, like, but Irina calls her course as continual learning. So there is a continual learning course at UDM, the like coming winter semester. Okay, so which you can take. If you are more interested in theoretical aspects of reinforcement learning, okay, like more towards optimal control and like approximate dynamic programming and like optimization for reinforcement learning and so on. Like, so there is a very mathematically heavy theory course on oral, like, so which is probably like a very advanced reinforcement learning course, like by Pierre-Luc at UDM. So the oral course, I don't know the name of the course exactly. Is it oral and optimal control? Like, I don't know the name of the course, but there's only one oral course at UDM. Okay, at UDM, but this is only in fall. So you have to take it next fall. Okay, I think these are the two relevant next steps. Okay. If you want to pick up the most recent advances in reinforcement learning, you also need deep learning expertise. Okay, so because a lot of innovations in reinforcement learning nowadays is because of deep learning, like revolution in the last 10 years. So there is a deep learning course at UDM. Again, like it's offered in both fall and winter nowadays. Okay, so I think it might be too late to register for winter because this course is really famous. Like if you can't get a seat, you can try for the next year. Well, probably I think this is mostly the next set of courses that you can do next semester. Like if you want to pick up more on okay. However, there are also a lot of other interesting online resources that you could look at. It's not very valuable that I write down the online resources here. Like I will probably send a list of all these things, but I'll just give you a rough idea. Like, so there is actually an oral course lectures by DeepMind, which is kind of currently the best place to do reinforcement learning. And they released this year's edition. Like, but my guess is there's going to be a huge overlap with the course. Like, so probably I will not recommend this. Like, it's if you want a good revision, you can do that. Okay, there's a huge overlap. But a very perfect next course for this, which is what I want to teach, but I will not be doing it this year, is actually the deep oral course by Sergey Levin at UCB. Okay, so he just released lecture. He's releasing lectures for his current fall course on deep reinforcement learning. All the lectures are available online, and it's an excellent second course for following up with this. Okay, so if you are very serious about doing reinforcement learning in the future, this is the perfect next course for you. Like, so, like, it kind of starts from where we stop. Like, so, like, the deep oral course talks a lot about deep reinforcement learning and like things like multitask learning, meta oral, like a bunch of other advanced concepts. Okay, so now you have all the background. Probably you will appreciate the course more if you also have deep learning background. So that is why you should do a deep learning course. But there are plenty of deep learning courses available online if you don't want to wait till doing this course. Like, but if you already have some good idea about deep learning, then like you can directly take the deep oral course. So I think in terms of textbooks, like Sutton and Bartow is the primary textbook for reinforcement learning. Like, I can't think of any other alternatives. But if you are really interested in the math, there's a lot of good old resources which are already in our references, right? Like, so things like neurodynamic programming or oral and optimal control and so on. So, but I'm sure it is worth reading Sutton and Bartow again and again, at least for 10 to 20 times. Okay, so back to back. So it's such a good reference for getting the fundamentals of the field. So, I think I will stop here and take questions. Yeah.
At what point you can say like an agent can generalize? Let's say if you have an 50 Atari games, and then like are 2 games or 5 games or 7 games, or like.
Well, I think it is very hard. So there is also a lot of work in machine learning nowadays on scaling laws, like, so where people talk about like what happens if I scale the compute, what happens if I scale the data, like what happens if I scale the size of the network and so on. Okay, like a lot of these scaling laws kind of hints that as you scale things, a lot of problems which are difficult at low level like scales like becomes less difficult. Okay, now, we did not talk about multi-agent reinforcement learning at all in this course. Okay, I wanted to touch multi-agent or like, but we did not touch multi-agent at all. So far, like all our discussions are based on one agent trying to learn a task, right? Like, so what if there are many agents in the world and they are all trying to learn the task? Okay. Now, in the multi-agent learning literature, it's kind of known that it is very difficult to learn with 2 agents than 200 agents. Okay. So when you are at scale, like 1,000 agents, like, so it's easier to learn things than like when you are like with just 2 agents. Okay, because a lot of problems gets magnified at lower scale. So it is not very clear like at what level like the agent is generalizing. But what I can say with a little bit of confidence is, as the agent sees more and more tasks, its generalization ability is going to improve. So like doing many things. So here's the thing. We need bottleneck to learn useful things. Okay, so if you don't have any bottlenecks, like we don't learn. Like, so like for example, if I don't give you assignment deadlines, like you will never learn. Okay, so like imagine like I teach this course with no assignments, no exams, and you just need to attend the lectures. Well, looking at this crowd, I can recognize all your faces. So I guess some of you would, or most of you would still attend the lectures. Like you're very sincere. But in general, like think about like a class of 200 students and like there's no exam. No exam, no evaluation. You just attend the course and there is no grade. Okay, so how many students will show up? Right? So we need bottlenecks for anything. So I think putting this extra bottleneck that you have to do many tasks, it's actually a very good bottleneck, because now the agent has to learn only things that it will generalize. Anything that doesn't generalize is not useful in long run, right? So like I think learning many tasks helps in generalization, but it is also very hard to learn many tasks.
Give an example where 200 agents solve a task easier than 2 agents, like a rough comparison.
Well, I don't have an example.
Because generally, the more you scale, the more harder it becomes, is what I have seen.
Yes, but some problems becomes easier. I don't have a good example right now, but I can find some examples and send to you. There is also a question in the chat. There are a couple of questions like, so what is the difference between continual learning and online learning? Okay, well, the pure form of continual learning is also online learning. It is just that online learning could be like just one task you can learn, you're learning online. While continual learning is an online learning setup where you're learning many tasks at the same time. So there is a lot of connections, but they are a little bit different. There is also a question, more fundamental question of why is theoretical math heavy knowledge useful? Okay, well, I think, okay, so I think both math and intuitions are important, not just intuitions. Okay, so like intuitions are useful for you to appreciate the idea, but like if you want to develop new ideas, like you need a very strong and precise framework to pose your questions and answers. Okay, so math gives us that precise framework, so it is very useful if your goal is not just applying these things. Okay, there is a question. Oh, okay, yeah, that's actually okay. I didn't know about it. It seems there is a suggestion from the students. Like there is also a course on game theory at UDM in winter, which talks about multi-agent RL. Yeah. Okay, and there's a question asking for solutions for the assignments. No, we cannot give solutions for the assignments. Like so you can come talk to me or to the TAs asking us like how to solve the problems in the assignment, like, but we cannot give solutions for assignments. Okay, so any other questions? Yeah.
This generalization is like kind of a trade-off between an agent performing on one task versus multiple tasks. So will there be a trade-off, or like it can still match that?
Well, there is a trade-off while learning options, for example, right? Like so, like sometimes, as I said before, like sometimes you have to lose something now for gaining something in the future. So that is very hard for agents. Like, so like, because most of the algorithms that we have seen are myopic in their view. Okay, so like they are not that far-sighted to say, for example, like do something now. Like for example, let's say there's a video game where sometimes you have to lose a life to get a key. So then you can solve the task in the next life. Okay. Let's say you're jumping, you have to jump to a knife. On the way, you get a key, but you can solve the task. I think there are games where you have these kind of things. Okay. You have to lose a life and you have 5 lives, let's say. It's going to be very, very hard for a reinforcement learning agent to pick up the strategy that it has to lose a life to pick up pick up a knife, right? Like it's because of the discounting factor and like various other things that we have here. So it is like coming up with generalizable representations or options or policies very hard. So there is of course a trade-off. Okay, any other questions? Well, I think if there are no more questions, this is the end of the course. Like, so I would like to thank everyone like who came to the class either in person or remotely, like very sincerely, like so. And also I appreciate the fact that like you kind of understand that it is the first edition of the course and there is going to be a lot of glitches. But I hope to have much more smoother second edition, like so, like with lesser load, like based on the feedback. But overall, like I really enjoyed the course. Like I hope you did that too. So thank you. So if there are no more questions, we can stop now. And it's my office hour. So if you have any questions, you can talk to me now. Like if somebody is, I think we have the room for 20-30 minutes. Like, so if somebody asks us to leave, I will go out. Yeah.
For the presentation, we have said 5 minutes.
Yeah.
Presentation in 5 minutes.
Yep.
Is it like a strict time limit, or do you have any guidance like what is that we have to cover it in 5 minutes? Because 5 minutes is.
Well, it's like a spotlight. Okay, a lot of conferences and workshops have spotlights. Sometimes they give you only 2 minutes to present your paper. So 5 minutes, I think, is definitely a doable time for presenting the course project. Like, so, like what I expect to see is like what is your contribution. So, like, also I think maybe one tip for everyone is like you're presenting only to me, right? Like, so you're not presenting it to a general audience. So I know what you're working on. So you don't need to spend time in introduction too much. Okay. So like you can directly jump to like what is the problem very quickly and what is your contribution. Like I really want to see your contribution for the project. Like I don't want you to motivate. For example, let's say somebody is working on double Q learning. I don't want you to motivate what is double Q learning. Like, so like I know what WQ learning is, like, so like you can directly start with your contributions in that case. Okay, so but of course, like if you're working on a research project, then maybe you need to motivate like what you're doing, why you're doing, and like how is it different from the literature. But for most of these ablations and like reproducibility tasks, I know the paper, like I know what the problem is, so you can directly jump to your contributions. So okay, anything else? Yeah.
These courses are, how many of them are in English?
Okay, all of them are in English. All of them are in English. But I think sometimes maybe the deep learning course might be in French. No, it's in English. Okay, so I think all of them are in English.
Taught by 2 different professors in fall and.
Yeah. I think nowadays it's taught by Aishwarya in fall and like Aaron in winter. So like, there's too much demand for that course. Like so. Okay. Okay. There's a question in the chat about what sort of effort should be considered as a contribution. Well, if you have a question about whether something is a contribution, then probably it's not. So I don't have a clear answer. So anything that involves your time and effort. Okay, so probably I will stop the call now if there are no more questions from the chat.